let's talk about required practical number 5, the effect of concentration on rate. Well, really, this comes in two parts. There is the so-called disappearing cross experiment, and then there is the chalk and acid experiment. And we are going to look at the chalk and acid one first because it's more complicated, and we'll just get that. We'll get that going straight away. So what do you do with this one? Well, what you do is you take some calcium carbonate and you react it with an acid, like hydrochloric acid, for example. And that will make a salt, calcium chloride. It will make water, and it will make carbon dioxide gas. Now, if we want to look at the rate of this reaction, we've got to look at how fast are the reactants being used up, or how fast are the products being produced. So with this one, it's much easier to look at how fast carbon dioxide as a product is being produced. That's the easiest way to do this. Now, just looking at this in symbols for a second, calcium carbonate is CaCO3, plus hydrogen, which is going to be HCl. Sorry, hydrochloric acid, which is going to be HCl. And then you've got calcium chloride, CaCl2, plus water, going to be H2O, plus carbon dioxide gas, which is going to be CO2. Now, hopefully you can see that this is pretty balanced, with the exception of the chlorines and the hydrogens, you see. So what we're going to need to do is just very simply balance this up by putting a 2 here, so we've got the same amount of atoms on both sides. Okay. So like I said, the easiest way to measure the rate of this reaction is to look at how fast carbon dioxide gas is being produced. But how do you do that? Well, you're going to need some equipment. You are going to need one of these, which is a conical flask. And one of these things, which is a gas syringe. And thank you to the lovely people at Wikicommons for those photos. So what do? Well, you get your conical flask and you put a bung in the top, like so. And then you attach it with a tube to the gas syringe. Now, the gas syringe does exactly what you think it does. It fills up with gas produced by the reaction, and then this plunger thing just gets pushed out further that way. And every now and again, you look at the results just there. Okay, and you might do it every, I don't know, 10 seconds, 20 seconds, depends on the exact way you've set up your experiment. So your chemicals go in here at the bottom here. So this would be your calcium carbonate and your acid. And you mix them together, stick the bung in and start the timer, and every, I don't know, 10 seconds you measure the volume using your gas syringe. It's the most accurate way available in schools to measure volumes of gas. So you could do this using that equation we looked at last video rather, which was the mean rate equals the rate. Let's try that again. The quantity of product produced over time. And it may well be that you got, I don't know, 50 centimeters cubed of gas in, I don't know, 10 seconds, which would mean that your rate would be 5 cm cubed per second. And that's fine. But if you look at the data every 10 seconds and you plot that as a graph, you get a bit of a better picture of what's occurring. So here is my graph axis. Here are my graph axes. Up the side is going to be volume of CO2. in the gas syringe, and that is measured in cm cubed, and along the bottom it's going to be time in seconds. Now if you plot this out, the graph will have this shape. This is a sketch graph. I'm not using any exact values, and that is a proper term, sketch graph. I'm not using any values to do it. I'm just going to draw the approximate shape. It will look like that. Okay. So why does it slope off? Why does it go flat? Well, by the time you get to here, where the graph has gone flat and the volume of gas produced is no longer changing, all the reactants have been used up. And the reaction has essentially stopped. And here, where it's slowing down, most of the reactants have been used up. Okay, now as you can see, if I just refer backwards, this is the mean rate. So this is like the average rate, and that's not especially good with this because you've gone from very fast at the start to stopped at the end. We need to do something a little bit cleverer. What if we wanted to find out the rate at a specific point? Well, for that, we're going to have to find the gradient of our line. And how do we do that? Well, I'm glad you asked. Let's get out the ruler and I will show you. So let's say that I wanted to find the rate at this, oops, so I want to turn my trusty ruler off for a second, at this point here. Right, so I get my ruler and I put it on the line like so, and I draw a tangent against the line like this. Now the exact size of the line doesn't matter because what we're really looking at is the ratio of how much the time changes to how much the volume changes. So I'm going to turn this into a triangle now because I'm going to work out the gradient of this line like so, and then we'll just rotate the ruler around another little bit. Oops, is that straight? Straight, perfect, like so. Okay, so you have your, there we go, perfect. Right, so you've got your tangent line now, and you've turned it into a right angled triangle. So what we're going to do is we're going to use that to find out how much the time changed and how much the volume changed during this little triangle. So you would read off your triangle from both ends. So we're going to look at it here, coming straight down, and let's say that this line here, following it down, touched at 10 seconds because it's a time. And then let's say that I followed this line down here, like so. And let's say, for the sake of argument, that touched down at 20 seconds. That means that the distance between these 2 points here against my x-axis is 10 seconds. Okay, so the change in time was 10 seconds. Let's do the same with our change in volume using the other bits of the triangle. Like so. So we're going to have a line coming across there, and we're going to have another line coming across there. So again, I'd look at my axes and I would guess, I would look at the scale. So let's say over here it touched at 20 centimeters cubed of gas, and up here 40 centimeters cubed of gas, and that means that this distance here is going to be 20 centimeters cubed of gas. So our change in time is 10 seconds, and our change in volume would be 20 centimeters cubed. So what good does that do us? Well, if we want to work out the rate's going to be the change in volume divided by the change in time. Okay, that will lead us to have 20 centimeters cubed over 10 seconds, which means that the rate will be 2 centimeters cubed per second. So at this specific point here that I put a line at, the rate is going to be 2 centimeters cubed per second. Okay, so that's required practical number 1. You've made some gas, caught it in a syringe, measured some results, probably done a gradient, the gradient of your tangent there, to work out the rate at a specific point. Required practical number 2, this is the so-called disappearing cross experiment. And this hinges around a reaction like so. It's a chemical called sodium thiosulfate. Perfect. And then you add some hydrochloric acid to it. And then it makes sodium chloride, so a salt, sodium chloride. And it makes water, and it makes sulfur dioxide gas. It's a bit smelly, this one, and it makes particles of sulfur. And again, we need something to measure. We could measure the rate at which sodium thiosulfate or hydrochloric acid were being used up, but the easiest thing would be to measure the production of this sulfur. You have solid particles of sulfur being produced, and if you want the technical term for that, that would be precipitate. There is a precipitate of solid sulfur particles. Now, that means that it's going to get increasingly cloudy over time, and you can use this to measure the rate. So what you do is you get, oops, where's my circle tool gone? You use this to measure its rate. So what you do is you draw a circle like so, and then you get a conical flask, you mix your chemicals together, and then you stick, turn the circle tool off, and then you stick it on top of this cross. And what happens is that over time the reaction occurs in the conical flask and it gets increasingly cloudy, and then you can't see the cross as well because of all the particles of sulfur in the way. And gradually over time, the concentration of these solid sulfur particles, this precipitate, builds up and builds up and builds up. And as soon as you can't see the cross anymore, you stop your stopwatch. So it's literally how long it takes the cross to disappear from your view because it is being obscured by this precipitate of sulfur. Okay. That's it, really. It is a very simple experiment. So let's look at likely results then. So with experiment number 1, this was the chalk and acid one. You will find that if you increase the concentration of the acid, so if you make that more concentrated, then the rate of gas production will be faster. So, if you increase the concentration of the acid, well, what's going to happen as a result of that? Well, you are going to have more collisions per second between the chalk and the acid, and more collisions per second will mean a faster rate, and also a faster rate of CO2 being produced. Experiment number 2, that's the disappearing cross. If you up the concentration of a chemical, let's say your sodium thiosulfate, sulfate, then you are going to have more collisions between the sodium thiosulfate particles and the acid particles, and then that will lead to an increase in rate, which is going to be a decrease in time for the cross to disappear. So with both of these experiments, really the take-home message is more concentrated chemicals react faster. Thanks.